Yeah, I know this.
Okay, so we are delighted to have Daniel Harlow from MIT visiting us today. And Daniel's going to be telling us about quantum mechanics and observers for gravity in a closed universe.
All right, so thanks for the invitation. It's nice to see old friends and also meet new ones. Do I need to, let me, hey, I clicked OK. So then it's not me, it's someone else has to click OK. All right.
Try using the mouse.
Oh yeah, I see, okay. I see. If I do that?
Yeah, you got it.
Okay. All right, I think it should be okay. All right. It's the, I think I can, oh yeah, there it goes. Okay, good. All right. Yeah, so I'm going to talk about this kind of general sounding topic of quantum mechanics and observers for gravity in a closed universe. Yeah, so I'll confess right at the beginning that this is, if there's some scale that measures crackpottiness, for me, this talk is probably the furthest out I've been on the scale. I think it's still reasonable. And we'll see if I can convince you, but, feel free to speak up and ask questions. I'm not necessarily like 100% convinced of everything I say in this talk either. So I'm happy to discuss. What we're going to do is think about a rather confusing issue that's come up in recent years among those of us who think a lot about the quantum mechanics of black holes and holography. So I would say we now have a fairly robust framework for thinking about the mathematics of the black hole information problem and the emergence of the space-time from the black hole interior that's been developed, say, over the last 10 years. I wouldn't say we know the answers to everything. I wouldn't say we solved all the problems, but we've learned a lot, and at least there's some picture for how these things should fit together. And the slogan, which I'll review in a little bit, is that is there some very loud? Okay, it's this cost of doing business. Okay, that's fine. All right, that's fine. I can take it. Yeah, so the effective field theory of the interior is what I'll call non-isometrically encoded into the microstate degrees of freedom of the black hole, which leads to a page curve, which is the entropy of the Hawking radiation as a function of time that's consistent with unitarity, as you can check using the quantum extremal surface formula. So that's summarizing a bunch of work over the last few years, which I'll review a bit more in what comes. But I think it's time for us to at least try to see what we can learn about quantum cosmology by taking these ideas that we developed in the context of black holes and applying them to the universe as a whole. Okay. Let's see what we get. So unfortunately, if we do this, it leads us to a rather puzzling situation, which is that what we find is that the Hilbert space of quantum gravity in a closed universe has dimension 1. So in other words, if you do quantum gravity in a closed universe, there are 0 degrees of freedom. Okay. So as I said, this talk is going to be a little bit crazy because I'm trying to deal with something that's crazy here. Okay, it seems crazy. So how can such a ridiculous thing be true, right? This just sounds ridiculous. Like, look at us, look at me, look at you. We don't have 0 degrees of freedom. There's all this fun stuff going on, right? So does that mean, for example, that we can just experimentally rule out the possibility that we live in a finite universe? Because obviously we don't have 0 degrees of freedom. But this is pretty crazy, right? It's saying we can learn something about the global structure of the universe without even bothering to look out the window. Right? We just kind of, in this room has no windows. Our lives sort of seem to make sense and not have 0 degrees of freedom. So, it just seems wrong that we can learn something about the global structure of the universe like that.
But I mean, we do know another thing, that we don't come from a fluctuation of a thermal equilibrium state, even, you know.
Yeah, that's right, and that's an important part of the story. I agree. That's something that we know, and in some sense, that does tell us something about the universe. That's right. Yeah, that we're not Boltzmann brains. But if this is not true, if we can't rule out, you know, if we could in fact be living in a closed universe that's just very big, you know, then we have this problem. How can we fit the richness of human experience into a one-dimensional Hilbert space, right? It sounds ludicrous. You know, and to make that more precise, right? I mean, what's wrong with doing effective field theory in a closed universe, right? We can certainly do effective field theory in a closed universe. There's more than 0 degrees of freedom. You know, it leads to predictions that are consistent with the experiment. So what's the mistake in doing that? And, you know, also, is there a mistake, you know, or could there be a mistake in the argument, right? You know, could it be that this argument that the dimension is one, you know, is one is just wrong? Could be, right? You know, maybe that's what most of you are hoping. But if so, then what's wrong? You know, then does this ruin all the nice stuff that we learned about black holes over the last few years? Yeah, and maybe that's a price that's worth paying, right? Maybe the one-dimensional Hilbert space is so bad that we should just accept that, you know, all this stuff we thought we learned about the page curve and you know, the emergence of the interior and being encoded in the radiation and all these things is just wrong. You know, maybe that's the price we have to pay. But I don't want to give up on that yet. Okay, first I'm going to try to save it and then see what I can do. And so this talk will be my attempt to just sort of see what I can do to save the black hole, you know, without giving up on we could be living in a closed universe. And so, yeah, so far, most people in the field, I would say, just seem to be hoping that the problem would go away. And that was my attitude for a while, too. But, you know, you can only be an ostrich for so long, right? I mean, if the theory is telling you something and you don't like it, then either you need to change the theory or you need to change yourself and accept it. You know, that's how it is as a scientist. Can be different if you're a voter, I guess, but if you're a scientist. So my current feeling after some evolution of my perspective is that maybe this is an opportunity. I'm not sure, but maybe it's an opportunity. Maybe, you know, to fix, you know, such a severe problem, we need to do something crazy, right? To deal with a zero-dimensional universe, you know, 0 degrees of freedom, we have to do something crazy to fix that. And if the crazy thing is correct, well, you know, when crazy things are correct, that teaches us something deep about nature, right? Like, you know, like quantum mechanics is crazy, you know, special relativity is crazy, right? I mean, these things were crazy, but they were also correct. And maybe there's some crazy thing that needs to be true here in order to make sense of quantum mechanics in a closed universe. So the proposal that I'm going to try to sell today is that in order to fix this, you have to explicitly include the observer, yourself, or your friend, or maybe you and your friend, as part of the universe, you know, explicitly modeled in the degrees of freedom of the system. And moreover, you have to force them to be classical by erasing the quantum coherence between them and the rest of the universe. And I'll give you a way of doing calculations where you can start with the one-dimensional Hilbert space and then do this operation of erasing the coherence between the observer and the rest of the universe. And in that way of doing calculations, you'll see that, in fact, the predictions of effective field theory are recovered, but only up to errors, which go like e to the minus the entropy of the observer. Okay. Now, in physics, as we've practiced it so far, the entropy of the observer does not appear anywhere, right? We have the theory that describes a system that's being studied, and the observer is external to the system. And we don't say anything about the observer, right? The rules say, oh, well, we're the observer, and they tell you what calculation to do with the system, but the entropy of the observer never shows up, you know, when you compute the level of the hydrogen atom, right? Like, you know, in what order, you know, in the fine structure, do you get corrections that are of order eta minus S observer? I never saw corrections like that in quantum electrodynamics.
But yeah, you would see them if you cared about interpretations of quantum mechanics and decoherence and measurement and so on.
Right, and that's kind of where we're going. Yeah, that's right. But in the way that I learned it in school, you know, the spectrum of the hydrogen atom is defined mathematically in a way that doesn't depend on the entropy of the observer. So I want to emphasize that, you know, and this is kind of getting at what Matt was just saying, that, you know, for reasonable sized observers, corrections which are of this order are large compared to non-perturbative quantum gravity corrections, you know, which in quantum cosmology would go something like, so L cos is like some cosmological scale here. It could be the de Sitter scale. If you're living in de Sitter, some scale that sets the size of the universe, then you would sort of generically expect that non-perturbative quantum gravity would go like in 4 dimensions would go like e to the minus L cosmology squared over G Newton, you know, which in our universe, you know, this is much smaller than that, right? Because, you know, S observer is maybe 10 to the 23. And the de Sitter entropy, I always forget whether it's, I guess it's 10 to the 60, not 10, no, 10 to the 120, 10 to the 120, yes, 10 to the 120. So this is e to minus 10 to the 120, and this is e to the minus 10 to the 23. Okay, so this one is much bigger than that one. So in fact, you know, so these observer dependent corrections can and indeed have to persist in the limit that G goes to 0. Okay, and so the effects that I'm going to talk about in the end aren't necessarily tied to quantum gravity. You need quantum gravity to argue that S observer can't be infinity, right? If you turn off gravity, you can take S observer to infinity, and then these corrections go away because you just make the observer really heavy, and who cares? There's no gravity, so doesn't hurt anything. But in principle, if you keep the observer entropy finite and take G Newton to 0, which you can do, gravity is not important for us biologically, it's not very important. Then these corrections persist. And so in fact, what you can think about what I'm talking about is corrections to just quantum mechanics, even without gravity, which vanish in the limit of an infinitely big observer. And in fact, my understanding of quantum mechanics has always been, although it's a bit embarrassing to say, but now I have to say because it's relevant for this talk, that quantum mechanics is an emergent theory that emerges in the limit that your brain is infinitely big. You know, if you're in a box with a finite number of degrees of freedom and you're made out of those degrees of freedom, there's a limit to how precise you can do things. You can't really measure, you know, probabilities to arbitrary accuracy. You can't really do calculations to arbitrary accuracy. And, you know, what we usually say is you say, okay, but the observer's out of the system and you just make them bigger and bigger, and, you know, then you can get whatever accuracy you want. But if the observer is part of the system, you can't. You know, and so things like the Born rule and so on, right? Like, I don't think they're really correct for an observer who has 10 to the 23 atoms and not infinitely many atoms. And we're going to have to deal with that in this talk.
But also in general, I mean, Born rules are all about probabilities. To check probabilities, you need an infinite number of variables.
Yeah, no, exactly right. Yeah, and so we need something better than that for a finite size observer. Okay, so I warned you this would get a bit crazy. Yeah. So sorry about that, but I'm sort of being forced into these issues by quantum gravity, and so I have to think about them. Okay, so just to spread the blame a bit, I'll mention that this is based on a paper with Misha Usayek and Ying Zhao. So Misha is a postdoc at KITP and Ying is a postdoc at MIT. So, you know, these two are brave, right? I have tenure, so whatever, I can say what I want, but I respect my collaborators. Okay, so here's the plan for the rest of the talk. So first I'll give some review of this idea of the emergence of space-time. I'm just trying to get that mouse thing out of the way. And the black hole interior, because that's what pushed us into this situation. So we have to think about it a little bit. Maybe not everyone thinks about this stuff all the time. I assume not. And then I'll review several of the arguments for why the Hilbert space should be one-dimensional in a closed universe. In fact, I'll give you 5 arguments. And it's not that I think the arguments are weak, so I give you 5 because I don't trust them, although maybe there's a little bit of that going on. But it's more just that I think it's valuable to see this come from a bunch of different directions and see how they all fit together. You know, because it makes it a little more tractable than if there was just kind of one argument and then there were other things that were in tension with it. Okay, then we'll have a little discussion about observers and decoherence and how you should think about observers in quantum mechanics. And then finally, we'll talk about how including the observer can, at least in some sense, give us a resolution of this idea that the Hilbert space dimension is one. So, so I like questions and discussion. As I said, this is a pretty, I mean, I have a bunch of calculations that I'll quote the results for you, but still it's a fairly fluffy topic. So I'm happy to hear what people think. But yeah, so maybe that's the end of the introduction. I'll stop here if there are any issues before we get into the sort of more quantitative things. Everyone is already convinced.
No, we want to arrive at point 3.
And arrive at 20. Yes. Okay, I'll do my best. Okay, so let's first do the bit of review. So in any quantum system with emergent behavior, we can formulate what we mean by emergence in terms of what I'll call the encoding map, which is a linear map from the Hilbert space of some effective degrees of freedom to some fundamental Hilbert space with, which is the degrees of freedom that the system is really made out of. So I'll start with some uncontroversial examples, right? So like in this little table here, they're phonons. And there's a Fock space of phonon excitations in the table, and we can have a quantum field theory of the phonons and scattering between the phonons. But really, that's just living in the Hilbert space of quantum electrodynamics. Well, really the standard model, but the standard model doesn't do too much. If we just have a proton and electron field, that's probably good enough for the table. Maybe neutrons also, I guess. So then, we can have this phonon Hilbert space, but then it gets mapped into this larger Hilbert space of the standard model or quantum electrodynamics. Not all the states in this Hilbert space are in the image of this map, right? Because, there are states in the bigger Hilbert space where there isn't even any table to begin with, right? And so those aren't going to be in the image of the map. So, only some of the states are in the image of the map. And that's kind of typical of any time you say something is emergent. What you mean is that it's only there in some approximation and only in certain situations, right? It's not there all the time. If it was, you wouldn't call it emergent. So another example we could talk about fairly similar is, the Hilbert space of pions gets embedded into the Hilbert space of QCD. So, here these are usually, we talk about them as low energy effective theories. So that's why I call this the effective Hilbert space here. So those ones are pretty simple. Another thing which many of us have thought about is if you take the Hilbert space of low energy excitations of ADS, particles zipping around in the vacuum, there's a linear map, an encoding map that maps that into the Hilbert space of some boundary conformal field theory. And again, the conformal field theory Hilbert space is bigger because, it has states where you have some huge black hole sitting in the middle of the bulk, and it's very far from just being perturbatively near ADS. If you want to think about the black hole states, you have to do something more complicated. Okay, but at least for the sort of simple states where it's just, little ripples in ADS, then we have this encoding map, which is injective, but not onto. And then finally, maybe the most controversial and the one that we'll have to revisit a little bit in the coming slides, is that if you do have that big black hole there, at least in some sense, we think there should be space-time inside of the black hole. It could fall through the horizon and live for a bit before falling into the singularity. And if the black hole is big enough, you could last for quite a long time. You could build the LHC back there. You could do precision tests of GR, and it would all need to work. At least that's what we think, if the black hole is big enough. And so somehow, again, I would like to say that there's some encoding map that takes that Hilbert space of effective field theory inside the black hole, and maps it into the fundamental Hilbert space of the black hole, which is something whose dimension is e to the area divided by 4g. Okay, the thing is the microstates of the black hole that you would count using string theory or ADS-CFT or something like that. So evidence for these latter, so these two, I think we all agree. Evidence for these latter two comes from a number of sources. So ADS-CFT certainly, well, here that's kind of obvious, but also here, when you think about the black holes in ADS, you can try to motivate this picture, also this quantum extremal surface formula, which is the formula for computing the entropy in the boundary CFT, but using the gravity description. And also the gravitational path integral, which has sort of become our primary weapon in some sense for trying to learn things about quantum gravity. Somehow the gravitational path integral, in ordinary quantum mechanics, the path integral is the same as the operator formalism, so there's nothing deep in it. It's just a sort of convenient way of doing calculations that preserves more symmetry. But in gravity, the path integral is really a different starting point for quantization, and it knows things that the canonical formalism doesn't know. For example, it knows the entropy of a black hole. You can do the Euclidean Schwarzschild to compute the entropy, but there's no way to get that by counting states of canonical gravity. So it's kind of an oracle that we use to learn things about quantum gravity. And one of the things we learn is that it kind of supports this encoding picture of the black hole interior. Any questions so far? Happy to. By the way, how strict are you guys about the time? I wasn't planning on going for a really long time. I'm just curious.
Very strict.
Very strict. That's fine. I mean, that's fine. I may be more strict about answering questions. So. Okay. So in particular, let me just discuss for one slide Hawking's information paradox, because I'll have to use it to motivate some features of a coding map for the black hole interior. Okay, so hopefully you've seen some version of this picture before. This is the Penrose diagram of a black hole in flat space that I formed by collapsing an infalling shell of matter. Okay, and this is the horizon of the black hole, the dashed line here. And the idea is you have these field theory modes on either side of the horizon that are entangled with each other because you want to be in the vacuum. You don't want anything strange to be happening right at the horizon. But then what we learned from Hawking is that because of this entanglement, you kind of have a thermal state for the external modes, or at least somewhat thermal. And that causes the black hole to radiate, losing energy. And moreover, since the entanglement here just comes from the vacuum structure here, it has nothing to do with this shell way over here deep inside the black hole. The radiation that comes out doesn't have any information about how you made the black hole. And so somehow that information seems to be lost, at least insofar as you can trust this picture of the production of Hawking radiation. And eventually the black hole gets small, it gets down to Planckian size, and you shouldn't trust this picture anymore, right up in the corner where the black hole is almost gone. But by then there's so little energy left that, whatever comes out, it's not going to be enough to return the information about the shell, because the shell could have been arbitrarily big at the beginning. And so that's Hawking's paradox, where he says somehow the information has to be lost. How you made the black hole will not come out in the Hawking radiation. So let's see what we can say about Hawking's paradox using this language of you have the holographic encoding map from effective field theory to the fundamental description. So here I've made sort of a cartoon of the Cauchy slice of the effective field theory degrees of freedom on the Cauchy slice here. It's the same as this Cauchy slice here on the black hole. So outside the black hole, you have some Hawking radiation modes that are going out. And then inside the black hole, roughly speaking, you have right moving and left moving modes. The right moving modes are the ones that are entangled with the Hawking radiation. And the left moving modes are the ones that keep track of how you made the black hole. So like this shell is made out of those left moving modes. So the information is in the left moving modes. And then somehow, but then the Hawking radiation is entangled with the right moving modes. So that's the effective field theory picture. That's the picture that leads to information loss. But what we want to do is imagine that there's some linear map V, which takes us from the interior modes to the microstate degrees of freedom. And I'll take the map to do nothing to the Hawking radiation, because the Hawking radiation is far away from the black hole. The gravity is very weak there, so nothing too funny is going on out there. So I imagine I have some map V that goes from the left and right moving modes to some fundamental Hilbert space that I'll call B. That's the Hilbert space of black hole microstates. And then just the identity on the Hawking radiation.
That's not true, right, for all black holes, because the part of the interior is encoded in the earlier radiation.
Yeah, well, you're about to see that. That's going to come out of this. Yeah, that'll come out of the properties of the map. So in this language, the way you can think about Hawking's paradox is indeed if the black hole is sufficiently old, then the number of field theory modes here in the interior is bigger than the number of microstate degrees of freedom of the black hole. So if I multiply the Hilbert space dimension of these two, it's bigger than the Hilbert space dimension of the black hole. So there's somehow not enough space in the microstates to keep track of everything that's going on inside of the black hole. And so Hawking's resolution to that was just you say, well, B isn't actually counting the microstates. So S equals A over 4G is wrong. And that's the information loss proposal for dealing with the problem. But we have pretty good evidence from string theory, from ADS CFT, that the entropy should be A over 4G. We can also just say black holes behave like they have entropy A over 4G, so it would be a pity if they don't. So let's imagine that they indeed do have entropy over 4G, but then now you learn something funny about this map V, right? Because then this map V is going from a bigger Hilbert space to a smaller Hilbert space. And a map that goes from a linear map from a bigger Hilbert space to a smaller Hilbert space can't be isometric. It can't preserve the inner product. And in fact, there have to be states that it annihilates. And it has to have a kernel. That's just a fact about matrices. Okay. The rank nullity theorem or whatever. So in other words, V has to be what we call non-isometric, in the sense of not preserving the inner product, which is different than the other three examples I gave of emergence, right? Here we would think the inner product certainly would be preserved, and it feels like you want the inner product to be preserved because in quantum mechanics, the inner product is physical, right? The probabilities come from the inner product. And so if you don't preserve the inner product, in what sense are you preserving quantum mechanics? In what sense is the fundamental theory actually, reproducing the quantum mechanics of the effective theory in some approximation? But here what we learned is that actually it can't, right? Somehow there, at least for some states in the interior effective field theory, they just have to be killed by this map. And then somehow we have to make sense of that. We have to decide, is that okay? Is that tolerable? Or is that a fatal objection to saying that this is what's really going on? So let me give a sort of more concrete model of that. So here's a model of a very non-isometric map. So here I use I. This is the combination of the left and right movers in the black hole. So I can be interior or island, depending what you like. People sometimes call it island. This B is the black hole Hilbert space. So the idea is I take my interior degrees of freedom. Just because it's convenient, I tensor it with some fixed state on some extra degrees of freedom. Don't think too hard about this. It's just to let me tune the dimension of the matrix as I like. I hit it with some big unitary transformation. And so far, if I have a unitary where I control some of the input and I fix some of the other input, that's an isometry. That preserves the inner product. So you're just saying only certain input states are allowed, but a unitary preserves the inner product for all states. So in particular, it preserves it for states of this form. But now instead of taking the full output of the unitary, I'm going to split the output and project some subset of the output onto some definite state zero, just because I want to for now. Okay. And then I want to view this as a linear map just from I to B instead of to the full output. And of course, this won't be an isometry anymore, right? Because if I try to do V dagger V, then this zero in the middle here gets caught, and I don't get to multiply the unitary U dagger U and cancel it. So this is a map that's not an isometry. And for now, just to get it to be sort of generic, I'll imagine that the U here is a sort of random unitary drawn from the Haar ensemble. So it doesn't have any particular special structure. So this model, although simple, it actually can reproduce most of the stuff that we like about the black hole information problem. So in particular, if you take this model and you feed into the input, Hawking's state, where the red movers are entangled with some reference system, and you compute the entropy of the radiation after applying this map, you get exactly this page curve calculation of Pennington, Almiri, Engelhardt, Meroth, and Maxfield, where you see that the curve goes up and then goes down, and the evaporation leads to a pure state at the end of the evaporation. And moreover, if you do some work, which I won't show you because it's not what the talk is about today, you can show that at least for generic U, although the map is non-isometric, it preserves the inner product for all input states, which are of sub-exponential complexity in the entropy of the black hole. Which basically means that if you're living in the interior and you only allow yourself to do experiments that have complexity that's not of order e to the entropy of the black hole, which is a ridiculously big complexity, then actually this will preserve the inner product up to exponentially small corrections. And that way you can sort of have your cake and eat it too. You can say effective field theory is good in the interior if you only do simple things. But the Hilbert space still fits into the Hilbert space of microstates. So there's no tension with unitarity. And so this sort of interpretation of these calculations is something we explained a few years ago with Chris and Netta and Jeff and Shreyabar. So this is all review. I haven't got to the closed universe yet, but I'm happy to, if there are any questions or comments about this.
For a very old black hole, or if you want a small black hole, almost at the end of the operation, the entropy is small, complexity is
Great
small.
question. There's the next slide. Okay, so it's instructive to consider the limit of a completely evaporated black hole, which is what Massimo was asking. So indeed, in this limit, the black hole is gone, so the entropy of the remaining black hole is small. But it turns out that because it's entangled with the Hawking radiation, the approximation is still good. If you want to get into a situation where the approximation is really not good, you have to also do a complete projective measurement on the Hawking radiation to get rid of the entanglement, and then you'll get large errors. And that's actually, I mean, from what I'm about to say here, we'll sort of see it. So let me just continue. So let's say the black hole is completely gone. So now here's the Penrose diagram for the fully evaporated black hole. So if we think from the bulk effective field theory point of view, what's a Cauchy slice at very late times? It actually has two parts. It has a part outside the black hole. Up here, there's sort of r equals 0 in polar coordinates because the black hole is gone. But then there's a piece of the Cauchy slice left over inside here. If because otherwise you could have a causal curve like this orange one, which would go through this region and it would never go through this slice. So it wouldn't be a valid Cauchy slice. And so if we take this model that I had before and we go to this limit that the black hole is completely gone, this encoding map here, it just becomes a rank 1 projection. The 0 projection is all that's left. And so in the evaporating picture, you see what's happening is I have this entangled state here. So this red line here, right, this is little r and big R. This red line here is this red line here in the encoding picture. So this R over here is the Hawking radiation. This is the interior right moving modes. Here are the interior left moving modes, which are orange. That's what remembers how we made the black hole. And if you look at this picture, if I feed in a pure state into the left moving modes, right, to collapse the black hole in a pure state, what happens? Well, it goes up here, but then it just gets projected back down here and it comes out as a pure state of the Hawking radiation. And so this is an evolution from a pure state to a pure state.
So is this like the final state proposal of Gibbons and
All the same. Yeah, so the mathematics of it is the same, right? So you have this projection and then you go up and go down and come out. But I think the interpretation is different because in their proposal, they were modifying quantum mechanics in the gravity description. And they never had a Hilbert space whose dimension is e to the a over 4g. They never had, string theory or microstates or anything like that. They just said in bulk effective field theory, you do post-selected quantum mechanics. So I think the physics of it is a bit different. For example, that violates causality, and I don't think this does. But the mathematics is the same. You go up, you bounce, you come down, and the information gets out. So now I want to emphasize that if we take this picture and we just look at the interior, we forget about the part outside, this is a closed universe. Okay, it's usually called the baby universe, where the information is supposed to end up if you believe the semi-classical picture. And if you look at this map here, what it's saying you should do is you should take the state of the closed universe, which is the left and the right mover modes here, and you should just do a rank 1 projection. And so that's exactly this dimension of the closed universe is 1. Right? You take whatever state you have, you just project it onto the one state that's real. Okay, if we just zoom in on this part of the diagram, it's a rank 1 projection. And so this is actually our first argument that the Hilbert space of a closed universe is 1. dimensional. You just take the limit of the completely evaporated black hole and you're left with this rank 1 projection. I'll have arguments that are more direct in the closed universe later, but I want to do this one first because you can see it as a limit of something that sort of we thought we understood. So far, so good?
I mean, it's a special closed universe because there was a singularity.
Yeah, that's right. So exactly. So the thing you complain here is you say, oh, there's this point here where I don't know what's going on, right? And indeed, so that's the weak point of this argument. And so then the other arguments I'll give you, they won't need to have that point there where we don't know what's going on. Yeah.
What about the system that does not evaporate, like the entire universe? If we have a closed universe that never evaporates.
Yeah, I'm getting there. I'm getting there. So yeah, you hear I'm doing the black hole first because the black hole is maybe more familiar for people who thought about this stuff, but I'm going to talk about the closed universe in a second. Yeah.
If it's closed, does the singularity point even matter? Like, would it not change entropy for the unitary matrix?
Well, I think it's still true that there's a closed universe here with dimension 1. But one could complain and say there's a point here where the effective description breaks down and maybe somehow that contaminates the argument. You could say that. Now I could say, okay, well, fine, don't go all the way to the end of evaporation, go till when the black hole has a 1,000, it is radius 1,000 in Planck units. So now effective field theory is still sort of good. And already the Hilbert space dimension is much smaller than it should be. But not 1. So to get to 1, I really have to go all the way, and you can complain a bit about it there. But the next argument I show won't have this issue. Yeah.
When you started with you, on top you had the 0 state.
Yeah.
Couldn't you just start, instead of just one single 0 state, a huge number of various states?
Yeah, you could, but if you allow anything up there, then it's an isometry again. So somehow the thing is, I wanted to in this map, right? I wanted this to be the Hilbert space whose dimension is e to the a over 4g. So for me, it's like an axiom that the black hole entropy is a over 4g, and it's actually counting microstates. So if you're willing to give that up, then you can just go with information loss. It's somehow I'm not willing to pay the price. Yeah. Okay. So yeah, now let's go to the closed universe. So I'll first try to interpret a bit here what I learned in the language of the closed universe, and then I'll go back and give the more systematic arguments for the Hilbert space dimension being 1-dimensional. So for now, I'll just assume you're temporarily convinced by this argument, and then I'll try to convince you more in a minute. Okay, so now let's leave behind the black hole and let's consider a smooth closed universe without this annoying Planckian region at the evaporation point. So inspired by the picture that I drew here, I'll just guess for the moment that I can take the encoding map to be like this. So I take the state of the closed universe here, I feed it in. Now, before I had a unitary matrix, now I actually want an orthogonal matrix. I'll explain that in a sec, well, it's written here already. I hit it with an orthogonal matrix, and then I just do one of these full projections onto a definite state. So this is a rank 1 projection encoding map, inspired by what we have with the black hole. The reason it's orthogonal is because if you're in a closed universe, all the states of the universe have to be gauge invariant. And CPT is always a symmetry. And in quantum gravity, there are no global symmetries, so CPT has to be a gauge symmetry. But CPT is an anti-unitary operator. So if psi is invariant under an anti-unitary operator, then I times psi is not invariant because the I changes sign under an anti-unitary operator. So I times psi is not allowed. So the Hilbert space of CPT invariant states is actually a real vector space instead of a complex vector space. And so I have to hit it with an orthogonal matrix instead of a unitary matrix.
But I thought that Witten says that that's not necessarily the case.
I had a lot of discussion with Edward. So the situation is similar to the situation with ordinary internal symmetries. So purely from the point of view of effective field theory, it's fine for an internal symmetry to be global symmetry. It can be global, it can be gauged, both are fine from the point of view of effective field theory. So what Edward is talking about in his paper is effective field theory. He's setting up the gravitational path integral, and in the gravitational path integral, CPT can either be gauged or global. So the claim here is that in holography, it's gauged.
So this is a case where the oracle is wrong.
Which oracle?
this magical box, the gravitational path integral?
I would say if you interpret the gravitational path integral holographically, it tells you there are no global symmetries. But if you just take it at face value, the same way you would when deriving information loss, then it says global symmetries are fine. Yeah, but you need to put in some holographic sauce. You can't just blindly use the path integral without at least a little bit of holography in your head. But you just write down a Lagrangian with a global symmetry. Why not? Do the path integral. It's fine. Yeah, I mean, it's similar to information, right? What happens is that if you throw a global charge into the black hole, if you're doing effective field theory, it ends up in the baby universe. That's fine. Still conserved. It's only once you convince yourself that actually all the information in the charge has to be out here that you have a problem. Okay. Good. So this kind of encoding map is clearly not a very good encoding map, right? Because whatever state you put in, you just project it onto this one state. And so surely in general, that's not going to preserve the inner product. How could it possibly, right? And so let's kind of confirm that. So we can confirm that by computing averages over the harm measure on the orthogonal group. If I just pick some generic O, it's kind of hard to do calculations. So you have to, if you want to do calculations, you have to average. And then you can sort of look at the slides of fluctuations to get you can sort of look at the signal to noise to get a sense of what happens for a typical fixed O. And so with the V, as I defined it, actually, if you just look at the average of the inner product between two states, psi and phi, it's actually fine. It gives you the effective field theory inner product. Great. But that can't really be true for a fixed O. For a fixed O, it's clearly not. And the way that's reflected is that in the calculation is the fluctuations in the statement are large. So you say, I look at the encoded inner product, I compare it to the effective field theory inner product, and then to make sure there are no cancellations, I take the difference and square it. Okay. And then what you find is that it's order 1, which means that for most states, psi and phi, the difference between the encoded inner product and the actual in the effective field theory inner product is order 1. Okay, so the inner product is not preserved. Okay, that's what these two equations tell you. And you shouldn't be surprised by this because this map is just projecting onto a fixed state. How can that preserve the inner product? And so our problem is what to do about this. Okay, how can we fix this? And so what I'm going to try to convince you is that by a careful treatment of the observer who's doing the measurements, these fluctuations that look order 1 here can actually be suppressed by e to the minus the entropy of the observer. And so it's a very sort of, the observer plays a key role in the story. You can't just abstract them out of the system. Okay, so that was it for the sort of emergent space-time review. I'm now going to try to give more complete and precise arguments that the Hilbert space is one-dimensional, because I do think I have to really convince you of that, or you'll never believe my crazy resolutions. But any more questions about the sort of black hole story, or kind of this story is the limit of it? You see, Massimo, I wasn't sure whether when you said the oracle, you meant the path integral, you meant Edward, or you meant Edward. So, yeah, so I had to clarify. Yeah. Let's record it. He has a good sense of humor.
So what is holographic sauce?
Holographic sauce?
Did I get that wrong?
Oh, yeah, what I meant is, yeah, the thing with the path integral is because it's not the same as the canonical formalism. If you just do path integrals in gravity, it's not clear what they mean. Because they're not manifestly equal to quantum mechanics, and in fact, they're not equal to quantum mechanics. If you in the cases where, so like if you're in low enough dimension, that the path integrals were normalizable, like if you're doing Jakob-Taubman gravity in +1 dimensions, the Euclidean path integral, if you try to come up with a quantum interpretation, the best you can come up with is that you say it's an average over many different quantum systems. So that it doesn't sound like quantum mechanics. But what we think is that probably there really is some fixed holographic theory that lives at the boundary that tells us what's going on. But then we have to interpret the path integral as some sort of coarse graining over those theories that live at the boundary. And if you say, I have this path integral, I don't know what it means, but I'm going to try to interpret it in terms of coarse graining over some boundary theory, that's what I mean by looking at it from a holographic perspective. And it's not always clear how to do that. I mean, in ADS-CFT, you know the answer, so that helps. But when you're not doing ADS-CFT, then we're sort of trying to guess what that holographic theory is. And so there's a bit of an art to it, which is part of why I said I'm not like 100% convinced by everything I'm saying.
And by path integral, you always mean the Euclidean rule?
I roughly speaking, yes, but I'm willing to analytically continue to Lorentzian signature. Yeah. But what I don't mean is take canonical quantum gravity and insert a complete set of states. Because that just has to be equal to the canonical quantum gravity, but that's not what people usually mean by the gravitational path. One could argue it's what they should have meant, but the other one gives such nice answers that we just, we can't give up on it. Okay, so let me, this won't actually be too long. So sorry, it's not going to be 20 more minutes of this, but I feel like I should at least tell you a little bit more what the sort of full strength is. Okay. I mean, as I said, after all, extraordinary claims require extraordinary evidence, unless you're Donald Trump. Okay, so perhaps the most insightful argument is also sort of the least precise. You just say, well, in holography, the fundamental degrees of freedom should live at the asymptotic spatial boundary, and in the closed universe, there's no asymptotic spatial boundary. So there should be no fundamental degrees of freedom. So I mean, this is the kind of argument where you could have said it 20 years ago and probably said it, someone did say it 20 years ago and everyone was like, yeah, okay. Okay, but if the statement ends up being correct, then this will be a correct argument for it. But you wouldn't just accept this argument by itself, okay? But I say it because it's good to be aware of it. Okay. I'm starting with the weaker arguments. Although in some sense, I think it's correct. Another argument that I'll mention, but not really get into because I don't want to get into what's a -1 form, but there's an argument from McMahon and Baffa where they argue that if there are no -1 form global symmetries, then that means that the closed universe Hilbert space should be one-dimensional.
Do we know what state it is?
Roughly speaking, it should be the Harlow-Hawking state. Yeah.
And can this, but if that state can be written as a sum of other states, at least in the old picture, why is that dimension 1? Or that's, I cannot write that state as in any other basis.
Yeah, so it has to do, right, so well, that kind of comes up in what I'm saying, because I have this larger Hilbert space of effective field theory states, and then I'm projecting onto the one state. So when I say that there's one state, it has two effects. The first is, of course, just saying, well, you have to be in that one state. You can't be in another state. So that all right, is an obvious conclusion of saying that there's only one state. But there's another thing, which is that if you somehow in the middle of calculations, you want to take the inner product of some of the other states. When you do it by just inserting this one state. So it's a rank 1 inner product. And so that's another effect of having one-dimensional Hilbert space. Yeah, we'll see this in the equations pretty soon. Okay, so I won't get into this one because I don't want to bother you about -1 forms. But also, I think this argument is a bit vague, I have to say, although again, probably it's correct. Okay, and then there's also the black hole argument I just gave you. So those are the kind of more hand-wavy arguments. Actually, I realize I'm giving you 6 arguments, not 5. Okay, so these are the kind of vaguer arguments. Let me now give you the stronger arguments, which, so there's one based on the quantum extremal surface formula, there's one based on the gravitational path integral, and there's one based on ADS-CFT. So you pick whichever of these you like the most, and then you can take the argument that's based on that one. So let's first do the quantum extremal surface formula. This is the simplest argument. So here's a closed universe, and let's say it has some degree of freedom S in it. It could be a spin or an atom or something in a closed universe. And in effective field theory, certainly we can entangle that spin with some reference system which is outside of the closed universe. Okay, I just prepare some entangled state with some system that's outside of the universe. What I'm instructed to do by Engelhardt and Wall is that if I want to know the entropy of the external system, I should compute the generalized entropy of all the possible entanglement wedges of S prime, and then choose the one which minimizes the generalized entropy. So here there are 2 choices. The entanglement wedge can just be S prime itself, or it can be S prime together with the whole closed universe. Both of those have the quantum extremal surface as the empty set, and then the entanglement wedge is homologous to S prime. And so what are the generalized entropies in the bulk? Well, for this one, it's just the entropy of whatever state I put here, because the entanglement wedge is just the reference system. for this one, since it's the whole system, this thing is purified by that thing, so the generalized entropy is 0. And well, since you're doing a minimum, 0 always wins at a minimum of positive things, so the entropy of S prime is 0, which means that an external system can never be entangled with a closed universe, because the closed universe has only one state, and so you can't be, every state is a product state. There are no entangled states. So that's argument number 1, no entangled states. There's a second argument based on computing the rank of the inner product matrix. So the idea is you have some set of states, say I, of the closed universe. You can define the inner product matrix of the states. And then the idea is you want to use the path integral to show that if you take this inner product matrix, it obeys the identity trace of m to the n equals trace of m to the n with the n in or outside of the parentheses for all integer n greater than 0. Okay, and if this is, for any matrix, if this is true, it means the rank is 1. Or if it has a rank greater than 1, this will not be true. Okay, so you're showing that the inner product matrix has rank 1. So here's the argument. We'll just check it for n equals 2, but the argument works for any n. So here, to compute the trace of m squared, I have my closed universes here, so I have 2 copies, and I contract the indices. Since it's a matrix multiplication, I goes with I, j goes with j. And then since I'm doing the path integral, I sum over whatever I can put in between those slices of the closed universe. When I do put the 2 outside, then I goes with I, j goes with j. But then, well, since you're summing over the ways of connecting the boundaries, the sum is invariant under permutations of the top boundaries or the bottom boundaries. And so these sums are just equal. It's just, this term equals that term. And whatever, did I get right? No, I didn't get right. This term equals that term. No, this term equals that. Oh, God, it's terrible. But I with I, where's I with I here? Is it? No, it's this one. Yeah, these 2 are equal. Right? And so yeah. So the 2 sums are equal. So indeed this equals that, and that's true for any m. When I draw the bars here, that's this annoying thing that I have to fess up to a bit. I mentioned it already. You should really think of the gravitational path integral as computing some kind of coarse graining average over what is not always clear. But in fact, you can also look at the fluctuation of this statement and see that it vanishes. And so the path integral will tell you that even in each instance of the ensemble, this equation is true. Okay, so that's argument number 2, using the path integral. Finally, and in some sense, this is my favorite argument, although it's restricted to negative cosmological constant closed universes. You can just use ADS CFT. So this one is pretty simple. So I want to compute the inner product of 2 closed universe states, which I can get, say, by insert, so I can prepare the states by using some Euclidean ADS boundary and then inserting an operator. So just view this from the bulk point of view. You can view this as a boundary for the path integral. You can extend the path integral into the bulk on some closed Cauchy slice. It's just being prepared by a Euclidean boundary in the past. And then if I want to compute the inner product, so in the path integral, I computed the inner product by this kind of stuff, but I can compute it exactly in the CFT. It's just the partition function with these 2 circles with the operators inserted. And hey, look, it's rank 1, right? It's a product, a function of I times a function of j. Okay. And so, and here there's no averaging, there's no funny business, right? I'm just doing ADS CFT, and you see, indeed, the inner product in the closed universe has rank 1. Okay, and so this argument I learned from my collaborators. So they had a paper last year explaining this. Okay, so that's it. That's it for the arguments. At least you're hopefully convinced that there are a lot of the arguments, even if you're not necessarily convinced by any one or subset of the arguments. I fought against them for a while, and I haven't found a problem yet. Okay, so so far we kind of have 2 ways of doing calculations. We can do calculations using the path integral, and we can do calculations doing this code model. So to be a little more precise, let's pick a concrete model of gravity so that we can really do the path integral instead of just drawing pictures. And so I'm going to pick sort of a very simple model of quantum gravity, 1 + 1 dimensions. The action in Euclidean signature is just minus some number S0 times the Euler character. And the Euler character is the integral of the Ricci scalar, so it's a gravitational action. But then in addition to just this sort of purely topological theory of quantum gravity that just weights, space-times by topology, I'm also going to allow some topological matter which lives on world lines that carry a species index I. Okay, so that I can have some matter in the closed universe that I can have this world line carrying an index. And so the dynamics of the matter are simply that the species index has to be the same at the start and the end of the world line. Sort of the dumbest possible dynamics, basically no dynamics for the world line. So in this model, we can just compute the path integral. So let's do it, and we can compare it to what we found in this code with the orthogonal matrix. So to compute the inner product, right, the idea is, I have some, I should have drawn dots here. I forgot to draw the dots on the train this morning. The dots are the ends of the world lines. So, you sum over the geometries that connect the two boundaries, and then to do the matter, you connect them using world lines. With the rule that if I connect a J external index to an I external index, then I get a delta IJ from the world line propagator. So let's compute just first the inner product IJ, and then I put the bar there to remind me I'm doing the path integral, so it's really an average. So if I just do inner product of J and I just get delta IJ because at leading order, because this I has to be connected with J, I get a delta IJ. And then at higher order, I can add handles and so on. That gives me corrections that are suppressed by this topological weighting factor S naught times the Euler character. But then the funny thing is now I can also look at the square of the inner product, and you see the square of the inner product somehow it gets more contributions than the inner product had, right? The inner product just had this one, but when I square it, naively I would just get these two contributions, but I also get from the path integral these ways where I can connect the boundaries the other way. So this is the kind of thing where in the canonical formalism you wouldn't draw those pictures, but if we're following Hawking's rules, then we should include them. And then if I do that, I get a fluctuation of the inner product, right? I can look at the inner product, minus the expectation value of the inner product squared, and then take the bar, meaning do the path integral. And I get exactly the same thing I had from the code. I get 1 plus the inner product of the states squared. Okay. And so this sort of topological model of gravity reproduces exactly what I had in this orthogonal, projection model of what's going on. And so in particular, you have this order 1 deviation from preserving the inner product. Okay. All right, so now hopefully you're maximally confused about the problem, and it's time for me to try to tell you about the resolution of the problem. Okay, so let's talk about observers. All right. So, I don't want to get into a long philosophical discussion about what's an observer. Is an electron observer? Is a ChatGPT an observer? Right? Okay, maybe at dinner we can get drunk and talk about that. But here I'm just going to assume 3 things which I think are fairly non-controversial about observers. The first is that an observer should have some Hilbert space with the dimension e to the s observer, and this is kind of what Matt was getting at before, they can only do experiments up to errors which are exponentially small in ES observer. If your brain can only hold so many digits of a real number, you can't measure something more precisely, with more digits than that. Okay. So that's assumption number 1. And so to get a better observer, you need a more entropic observer. Secondly, I will require that the observer is effectively classical. They're not really classical because they're living in a quantum theory, but they're classical to the extent that anything is classical in a quantum theory, which means that there's a pointer basis of states for the observer, which are stable under interaction with the environment. So this is the definition of what I mean by a pointer basis, but don't worry too much about it. It just means, basically you randomize the environment, you bring in the density matrix and the pointer basis, and what the interaction with the environment does is it kills the off-diagonal elements in the density matrix and does nothing to the diagonal elements. So that's sort of decoherence. Kills the off-diagonal elements. But it's a basis-dependent statement, right? This is not true in any basis. It's a special basis, the pointer basis, and that's the basis where you're classical. So it's like with Schrodinger's cat. It's classical on the basis where you're alive or you're dead. It's not classical on the basis alive plus dead and alive minus dead. And this condition is why not. Okay. And then finally, I will assume that the observer is indeed entangled with their environment in some state whose entanglement entropy is of order the entropy of the observer. And so this is the idea. Here I am sitting in this room. The photon is bouncing off of me. I'm looking at all of you. I'm very far from pure state. I'm quite entangled with an entanglement entropy, which is of order my total entropy. Okay, and so there's a nice review by Zurek from 2003, which discusses these things more. If you haven't thought about them before, they may seem a little bit strange, but I think they all make, I would say actually these are not too controversial. Okay, now this interaction with the environment is an example of what we call, but by the way, I have 28 slides, so I don't know, I'm getting there, but
Like in the next 10.
yeah, certainly in 10 minutes I can do that. Yeah. Okay, so the interaction with the environment is an example of what's called a quantum to classical channel. So a channel is a map from density matrices to density matrices. It's what quantum information people talk about as a generalized version of a unitary. Basically, it's a unitary on the system together with something else, and then you trace out the something else, and you get a channel. Okay. So this is a classical to quantum channel. It's just the thing I already said. It kills the off-diagonal elements of the density matrix and preserves the diagonal elements.
Of course, all the problem in the interpretation of quantum mechanics comes from this trace, because the coherence doesn't solve it doesn't interpret quantum mechanics, doesn't transform it to.
I agree with that.
I mean, it just tells you that it doesn't matter where you cut the observer. So as long as you have the coherence and entanglement with the environment, then no matter where you put the observer, whether it's ChatGPT or the observer ChatGPT, you get the same result.
Yeah, so I'm not saying I solved the measurement problem in quantum mechanics here. I'm just saying what I know about it.
Is this similar to ETH, that in the end you will only have the diagonal elements to compute expectation values?
The diagonal expectation value means that you have done a measurement. It's a bad way to talk about it. A wave function.
Yeah, so I think what I'm going to say, I'm about to say that in a second. So what the environment does is it erases the off-diagonal elements of the density matrix in the pointer basis, which tells you that to the extent that you don't have to worry about those off-diagonal elements, you can interpret quantum evolution as inducing an evolution of classical probability distributions. The problem, of course, is that somebody from the outside could totally recohere the state, right?
And no, so the problem is that in order to even define probability, you need someone from the outside that does a measurement.
Yeah, that's the problem we're having. Yes, that's exactly the problem we're having. Okay, and indeed, let me say another example of this is a measurement in the A basis, which removes the quantum coherence, leaving a classical probability distribution for the measurement results, which is given by the Born rule.
Well, if you assume the Born rule, again.
I have definitely not derived the Born rule. I'm not claiming to.
So you have a process of probability if you assume.
Yes, I agree with that. Yeah. So I mean, the philosophy here is essentially that I think that to be an observer, you have to tell yourself that your decoherence is irreversible, even though it's not true.
And also you have to be an observer. It's a little bit circular.
I mean, it's on to me, I mean, I'm kind of saying it's the definition of an observer is someone whose decoherence is irreversible.
Yes, that was also Heisenberg, by the way.
Yeah, so I don't think, I mean, I think it's not I'm not claiming I invented this rule.
But again, if you don't want to have anything outside, you have a wave function, so let's say many would, loosely speaking, right?
Yeah.
Well, then you have that your wave function goes from a non-entangled state of universe and observer to an entangled state.
Yes.
Still, it's a wave function to derive probabilities, blah, blah, blah.
Yeah, so I'm gonna have to do something about that.
Yeah.
Okay, yeah, I'm gonna have to do something about that. And it's gonna be in the slide after this one. Okay. So now let's include the observer explicitly in our closed universe code. Okay, so I take the code I had before where you take the state of the closed universe, you feed it into an orthogonal matrix, you project. Okay, what I've done though is I've split the effective field theory degrees of freedom into three parts: the observer, the environment, and then the matter that they want to do experiments on. And it's arbitrary. I chose to do that. Okay, so far nothing changed. I've just restricted the input in the map to say that I'm only interested in states where we've got this observer there, they're entangled with the environment in some way, and there's this system sitting there that they want to do experiments. So it's some subset of the initial states to the code that we had before, but this O is the same as before. So the one state is still here. It's this 0 in the O transpose. You know, this is like the bra of the one state here that we're projecting on. Okay. So let's compute the inner product between two states of this type. Well, here it is. Still rank 1. Yeah, you see it's a product of the thing on the top and the thing on the bottom, because you know, the observer is sitting here, but you know, so far I'm just treating them like another matter particle, you know, as somebody outside of the system would. And to somebody outside the system, the Hilbert space has dimension 1. Okay, and so I can't do anything with this. It still doesn't reproduce effective field theories. Okay, so here's the crazy claim. The claim is that the problem with this inner product is that it still treats the observer as a fully quantum system, the same as the rest of the matter. We're using the rules that are appropriate for someone outside of the universe looking at the system. But from outside, there's a one-dimensional Hilbert space because there's no one looking at you from the outside of the closed universe. Actually, we had a religious joke in the paper about that, but I won't tell you what it is. There's no one from the outside looking at. Okay, so here's the proposal. Okay, so we take this inner product that didn't work, and we take this little piece of it here, where we have this entangled state of the observer with the environment, and then we hit the observer with this decoherent channel in the basis where they're classical. So at this point, I'm breaking the rules. I'm proposing a new rule that I just made up. It's not quantum mechanics. The rule is that you have to take the observer and forcibly throw away the off-diagonal components of the density matrix in the pointer basis. That's what this map is doing, this channel C. And then I do nothing to the environment. I only do it to the observer because who cares whether the environment is classical, but observers are classical. That's what I learned from Bohr. Okay.
So this is a one-dimensional projection. It's omega is really.
This is a one-dimensional here. You see, right? Before I treat the observer special, it's still one-dimensional.
But even this projection.
No, this is not. Now it's not a product anymore, you see? So this thing, when I hit so this is a pure state before I act with the channel, but after I act with the channel, it's a mixed state. And so since it's a mixed state, that means the top and the bottom are now connected. So the inner product no longer factorizes. It's a mathematical fact.
I'm simply, I don't understand the notation.
Yes, so this C is this channel that I wrote before, this one, okay? So I throw away the off-diagonal components. So if you think you have two qubits, okay? And they're entangled, but then now take one of the qubits and throw away the off-diagonal components of the density matrix by acting with this channel.
So is this a projection of a diagonal state?
No, it makes a, maybe I have to write it. So sorry, this won't help with the time, but so before I do the projection, I have two sums, AA and BV. Okay, this is the state of the universe. Now let's act with the channel. So what that does is it gets rid of one of the sums by setting B equals A. So because remember when I act on, so this is the observer here, and this is the environment here. So the rule is I take this state, well, it's not a state, I take this operator on the observer, and then I throw away the off-diagonal components, but keep the diagonal components.
As if there was an observer outside the universe.
Yeah.
The decoherent state.
Yes, that's right. And so after I do that, I get A, which is a mixed state. And so that mixed state is the one that I was drawing here. Okay. And so since that's a mixed state, it's a matrix now that hooks the top and the bottom together, and it's no longer rank 1. So I've defined now an inner product on the matter system, which is not ranked 1. Okay, by making the observer classical. Now I can make this look more like what we were saying before. So this is just bending lines around. So I won't try to get into it too much. This is equivalent to saying that what I do is I take the matter system I define a map V hat that goes from the matter system to a copy of the observer's Hilbert space, where what it does is you take the state of the observer and you clone it in the pointer basis to the outside, and then to get this extra thing here, and then the inner product that I defined on the previous slide is the same as just taking V hat, dagger, V hat, acting on the matter system. So this is just bending lines around, it's nothing deep. It's the same as what I said before. And so by forcing the observer to be classical, what I've essentially done is I've created a fundamental Hilbert space for the system, OB prime, which is a copy of the observer Hilbert space, but is now outside the system. And so if you look at this map, information can now go from M to OB prime. You don't necessarily lose all the quantum information. I want to emphasize OB prime is not real, right? It's not like there's actually an observer outside of the system. The inner product is really this one, where I just did this map of making the person classical. But it's a sort of convenient fiction to use in interpreting the calculations that you do, that there's this external observer there that was created by making the observer who's in the system classical. Okay, so now almost done here. Let me just say the results. Really like 1 or 2 more minutes. So now let's see how this changes our previous calculations. Okay, so now you just have to trust me. We're not going to learn how to do Haar integrals in this talk. Okay, so you average over orthogonal. So this v hat, right? This map that goes from the matter system to the clone of the observer. As before, on average, it preserves the inner product, but we saw that that's not enough because the fluctuations could be large. But now the fluctuations are actually suppressed by the entropy. This is actually the second Rényi entropy of the entangled state between the observer and their environment. And so this is where it was important to assume that the observer was indeed entangled with the environment with an entropy which is of order S observer, by assumption. And so then this large fluctuations are now suppressed by e to the minus S observer, which was the central claim of the paper. So now effective field theory is good up to e to the minus S observer instead of just good up to errors of order 1. And so this is the key result. The bad consequences of the one-dimensional Hilbert space are suppressed by e to the minus S observer, provided we do this rule of enforcing decoherence on the observer. Because you're not an observer if you're not decoherent. It's the philosophy. You can also do the same calculation in the path integral, but I'll spare you the details, but in this topological model, but you get the same answer. So if you don't like codes, you can just do the path integral. I know a lot of people are allergic to codes and love the path integral, so this is the path integral calculation. You get the same answer. Okay, so a lot more I could say, but let me just make them general. That's the last slide. Right, so the bad terms in the inner product, they came from what you could call cross-connection geometries in the gravitational path integral, where the observer, like say in this picture that I drew here, the observer, somehow went this way and ended up in the other copy of the state from the one you thought you were talking about. That's where the bad stuff comes from, the contributions that you wouldn't have drawn in the canonical formalism. In a limit that you take S observer to infinity, you get a rule that just says you just shouldn't draw these cross-connection geometries. Okay, so there was a paper that came out the same day as ours, Total Coincidence, where they said that you should just throw away the cross-connecting geometries. I don't love that rule because if you take S observer to infinity, then you lose the ability to see the one-dimensional Hilbert space if the observer is small. And also if S observer is infinity, well, probably the observer is going to collapse into a black hole or something. So you probably don't really want an observer with S observer equals. But it's kind of, maybe this is by taking this limit, then they didn't have to say all this stuff about decoherence. They just said in the path integral, you throw away the cross connection. So if you're happy with that, fine. But I feel like then you don't really know why you threw them away. Okay. Now you might also, this I already said, but you could say, so this is kind of the one state, right? It's the unique state of the theory. You say, why did we consider any other states besides that one? So that's an old thing in cosmology. It's because when you do experiments in cosmology, you first have to condition everything on what you know about the universe and then do an experiment. And then that projects you off the state onto other ones, at least in the effective description. And then finally, I said this, this rule is a modification of quantum mechanics, right? In addition to you have to know more than just the one state, because it's just one state, right? And moreover, the Hilbert space is real, so it's a sign, plus or minus 1. And so if I just tell you plus or minus 1, you can't do physics. So you need to know something more. You need to know this map V. But I don't find it too bad because, as we were discussing anyways, quantum mechanics needs to be modified if the observer has finite size. So I can tolerate that anyway. And maybe this is part of how to do it. Okay, thank you. Sorry for going a little over.
So if you're modifying quantum mechanics, why should we believe that the arguments you gave that the Hilbert space should be one-dimensional, which were made, assuming at least some aspects of quantum mechanics?
Well, I would say in some sense, we're also modifying quantum mechanics in the black hole interior, just sort of less severely. So the thing that we're not modifying is boundary quantum mechanics. So that's kind of, that's sort of the whole philosophy of the information problem, is that you want to make the world safe for asymptotic quantum mechanics. You want the S matrix to be unitary. And if you're Bob Wald, you just say, well, that's a silly thing to want. You just work on Cauchy slice in the bulk. The evolution is obviously unitary. What's the problem with information loss? It's just the information went into the big universe. Fine. Okay. But somehow we have this idea from string theory or holography, or we want S to be equal to A over 4G, that we think there should be this boundary quantum mechanics that makes sense. And you could say, well, why do we want that?
Especially if we live in a closed universe where there is no boundary.
Well, right, that's exactly the problem, right? So somehow we have to decide, right? And we could just give up on holography. We could, right? Yeah. But there's so much nice stuff with holography, right? I'm not going to give it up without a fight.
But there was also another set of arguments saying that in closed universe, saying that the entropy is the area of the horizon.
Yes.
For GS. So yes, this is. So you say no, that's.
Well, yeah, so it has to do with whether you're thinking about the static patch or the global slices. So yeah, so that's something we're still working on, but I think there's a sense in which you can have your cake and eat it too. Where if you're an observer, so in de Sitter, the observer doesn't get to see the whole universe. They can only see part of it. And so I think the idea is that if you're living in the static patch, you can have an effective description of what you actually see that is more than one-dimensional, that has this static patch entropy, e to the S de Sitter. But then somehow if you exit from inflation and now can see the whole picture of the universe, you'll see that that was fake. And that if you look at the global slice, there's really just the one state, the Harlow-Hawking state. And this tension between the Harlow-Hawking state and sort of having thermal equilibrium in the static patch is a whole issue in de Sitter. But I wouldn't say we've completely nailed that. That's kind of what we're talking about it now.
But of course, you're seeing more than the universe in the Harlow-Hawking state. The Harlow-Hawking state is the only.
Yeah, it's the only state. And when you compute an inner product, the inner product is just insert the Harlow-Hawking state and nothing else, which is a pretty wacky. But that's what these arguments are telling us to do. So,
But again, to me, it seems that you're introducing a third observer from outside that does all these things.
yeah, so in some sense, mathematically, there's this OB prime, right? So it kind of is doing that. But I can present it by just all within the Hilbert space, all within the closed universe, but just having this rule that I have to apply this channel to make the observer
But
classical.
the channel is a shortcut for having an external system, right, that projects or
Yeah,
observes.
in the traditional way of thinking about it, that's right. But it's an operation I can just do in the closed universe. And so somehow the idea is to give up on saying you need to have the external thing to motivate it. You just do it. And as I said, I'm not 100% convinced of that, but if I do it, it solves my problem. And so that makes me happy.
And it's this operation, I mean, it doesn't conflict with other cases in other setting in quantum mechanics, let's say in a laboratory where.
I don't think so, because it's all suppressed by e to the minus S observer, right? So I mean, I think I am predicting that quantum mechanics breaks down at that size for observers of finite entropy, but we can't test it, right? Like we would need to be much worse observers than we actually are.
I mean, what's a little odd though is that this procedure is, some description of decoherence, right? So
Yeah.
approximately decoherence does this.
Yeah.
And the approximation is extraordinarily good. It's
Yeah.
by effects of order even minus S.
Well, it's extraordinarily good unless somebody recoheres the wave function. I mean, that's always the complaint with decoherence.
Yeah, that's very large,
So I'm just trying to, I think what I'm trying to say is that to be an observer, we should have a principle that nobody can recohere the wave function.
Right.
And so of course, I mean, somebody could, right? You could recohere my wave function in principle. But in the context of the operation where you did that, I'm just not a valid observer anymore. So for me to be an observer, we have to restrict to situations where nobody recoheres my wave function.
But again, I don't think that this is the only problem. You still have to derive the Born rule that here comes out of, it's an assumption.
I mean, I put it in, right? No, I mean, I had a rule that I
But
compute the
that
inner
rule
product.
only makes sense.
Yeah.
And it depends. I mean, in an instrumental point of view, only if there is someone that does the observation.
Well, yeah, I'm
In
trying
many words, we
to,
don't know how to derive it.
so I'm trying to propose a new rule, which is that you have this, code that you use. And you still use the inner product in the way you normally would in the Born rule, but you have to do this channel thing first. And so, I mean, it's different than the usual rule. It agrees with the usual rule up to correction like e to minus S observer. But the thing that's nuts is that if I don't do the channel, then it just disagrees at order 1. And so that's the thing that gravity is forcing on us, where it kind of forces us to grapple with this in a way where normally you just say, oh, well, S observer is so big, who cares? But somehow here, if S observer is big, but you don't do the channel, you still have an order 1 problem. And so that's why I feel like it's hard to hide from this.
You're sure it's an order one problem and things that you actually care about as a finite?
Yeah, absolutely. Yeah. I mean, so like in this world line thing, right? It's just one particle, it has an index, so, it's gonna be particle type 1, type 2.
Yeah.
And if you ask, in bulk effective field theory, right? Particle type 1 is orthogonal to particle type 2. But if you use the gravitational path integral to compute the inner product, it's order 1 between 1 and 2. Because of this cross connection where you can connect the other way and then find your friend. Yeah. So I mean, that's this gravity path integral, it's weird, right? But it also gives us stuff that we like. So I don't know. Yeah, I mean, either we give it up or we have to accept this and somehow learn to live with it. So I'm doing my best here.
Maybe let's say Daniel and anybody else.